Myself, I'm Ganga Bhavani, Assistant Professor in AC Department. So today we shall discuss about large signal amplifiers. We shall see what are the various types of large signal amplifiers, and then we shall study in detail about Class A amplifier. Okay. So why do we need large signal amplifiers or power amplifiers? Okay. So practical amplifier always consists of number of stages that amplify weak signal until sufficient power is available. Okay. So if we see small signal amplifiers, generally we have number of stages. Okay. In each stage, the signal is being amplified until the sufficient power is available to the output device. So first few stages in the multi-stage amplifier have the function of only voltage amplification. That is, in the first few stages of multi-stage amplifier, we will just perform voltage amplification. Okay, but the last stage is generally designed to provide maximum power. That is, power amplification is done in the last stage only. So what you call the final stage of multi-stage amplifier as power stage. That is the reason why you are calling it as power stage. So early stages build up the voltage level. So what we understood by this is early stages are mainly used to amplify the voltage level of the signal. Okay, while the last stage builds up the power. So that sufficient, which is sufficient to operate the output device. For example, if it is a loudspeaker. Okay, so we shall talk more about the final stage, that is large signal amplifier or simply power amplifier. Okay, so input signal to a multi-stage amplifier is generally small, a very few millivolts from a cassette or CD or few microvolts from an antenna. So first few stages of multi-stage amplifier will now perform the voltage amplification. Okay, the last stage handles a large signal, that is after being amplified from the previous stages, the input to the last stage will be definitely a large signal, and now the last stage is supposed to produce large amount of power in order to operate the output device. So for example, if you see this block diagram where input device is a microphone and output device is a loudspeaker. So microphone generally it handles signals of very low voltages. So first a few stages will be having voltage amplification, and the final stage will be the power amplifier, and output of power amplifier is then given to the loudspeaker. Okay, so basically power amplifier is used in last stage of the multi-stage amplifier, and its main purpose of using it is to increase the power of the signal so that it can be used to feed the output device. Okay, so small signal amplifiers handle small input AC signals. Okay, these are called as small signal amplifiers. Voltage amplifiers will generally fall in this category. So small signal amplifiers are designed to operate over linear portion of the output characteristics. So small signal amplifiers generally they operate over linear portion of the output characteristics. So the transistor parameters such as current, gain, input impedance, output impedance, all these do not change as the amplitude of the signal changes. Such amplifiers amplify the signal with little or no distortion. So since the voltage amplifiers operate in linear portion of the output characteristics, certain parameters such as current, gain, input impedance, output impedance, etc., these all do not change as the amplitude of the signal changes. So such amplifiers amplify the signal with little or no distortion. So with voltage amplifiers, we'll be having very less distortion. Okay, coming to large signal amplifiers. Those amplifiers which handle large input AC signals are called as large signal amplifiers. Okay, range will be among few volts, whereas in case of small signal amplifiers, it is few millivolts or microvolts. Coming to large signal amplifier, they can handle large input AC signals in the range of few volts. Okay, so power amplifiers fall in this category. Whereas in small signal amplifiers, voltage amplifiers are in the class of small signal amplifiers. Coming to power amplifiers, these fall in the class of large signal amplifiers. The large signal amplifiers are designed to provide large amount of AC power output so that they can operate the output device, for example, a speaker. Okay, main features of large signal amplifier or power amplifier are the circuit's power efficiency, maximum amount of power that the circuit is capable of handling, and the impedance matching to the output device. So main features of large signal amplifier are, first thing is efficiency. Okay, and then what is the maximum amount of power that the circuit is capable of handling, right? And finally, the impedance matching. Efficiency, then what is the maximum amount of power that the circuit can handle, and the last one is impedance matching. These three are the main features of a large signal amplifier. So in general, where amount of power involved is 1 watt or more, then the amplifier is termed as power amplifier. So amplifiers where the amount of power involved is 1 watt or more, then such amplifiers are called as power amplifiers. Okay. So in small signal amplifiers, main factors are amplification, linearity and gain. Okay, in small signal amplifiers, main factors that we consider are amplification, linearity and gain. Coming to large signal amplifiers, what are the main features that you are going to consider? Main factors: efficiency, maximum power capability and impedance matching. Okay, we shall consider these factors while discussing small signal amplifiers and large signal amplifiers. Then, classification of power amplifiers. How are you going to classify power amplifiers? So, power amplifiers are classified mainly based on for how much of the input, how much portion of the input the amplifier is going to conduct. Based on that, you have got basically four. Of course, you have class D also. Totally 5 types of power amplifiers: class A, class B, class AB, class C, and class D. Class A amplifier, what it does, the amplifier conducts through the full 360 degrees of the input. That is, for the complete one cycle of the input, that amplifier is going to conduct. Okay, such amplifiers are called as class A. Then the Q point is set near the middle of the load line, and even location of the Q point also will change. Coming to class A, complete 360 degree of the input the amplifier is going to conduct, as well as the Q point is set near the middle of the load line. Class B, the amplifier conducts through 180 degree of the input, that is only up to 1/2 cycle. 180 degree means it is nothing but 1/2 cycle. The Q point is set at the cutoff point. Okay. Class AB, it's nothing but a compromise between class A and class B amplifiers. Okay. So the amplifier conducts somewhere between 180 and 360. That is more than 1/2 cycle but less than complete full cycle. So the Q point also is located between the midpoint and cutoff point. That is, a midpoint is for class A and cutoff point is for class B. So for class AB, the Q point is set somewhere between the cutoff point and midpoint. Class C, the amplifier conducts less than 180 degrees, that is not even for 1/2 cycle. Less than 180 means not even 1/2 cycle. Q point is located below the cutoff level. Okay. Now class D, it's an amplifier that is biased especially for digital signals. So class D amplifier, it is mainly used for digital signals. So we shall be discussing about class A, B, AB and C. Okay. So we shall see just a diagrammatic representation of what we have discussed till now. Okay. Class A power amplifier, see here. Output is for complete cycle of the input. Output of class A amplifier conducts for the full 360 degree of the cycle. That is, for one complete cycle, the amplifier will conduct. And see the location of Q point. Q point is located here, that is at the middle of the load line, so that the AC signal can swing one full cycle. Okay, Q point is chosen at the middle of the load line. Okay, DC load line indicates maximum and minimum lines, limits set by the DC power supply. Okay, so if this is a load line, then Q point is located in middle. Okay, class B, as I told, it conducts only for 180 degrees or 1/2 of the AC input signal. So if you assume this is a complete AC input signal, then this blue line indicates for 1/2 cycle it is going to conduct, and for the remaining half it's not going to conduct. Okay, and Q point is located at the cutoff. So this x-axis represents cutoff point. Right, Q point is at 0 volt on the load line, so that AC signal can only swing for 1/2 second. Since the Q point is chosen on the load line, and Q point is at the 0 volts line, so what? 0 volt on the load line, so that AC signal can only swing for 1/2 cycle. It will swing only for 1/2 cycle. Okay. Coming to class AB, see if this is the input signal, What do you observe here in the output signal? And this is a DC line. See, this dotted line is a DC line. Then you see that it is conducting for more than, it is a compromise between class A and class B. So the Q point is located above that of class B but below that of class A. For class A it was at the midpoint. For class B it is on cutoff point. So compromise of these two. So what Q point is chosen in between the midpoint of the load line and the cutoff point. Okay. And the output conducts between 180 degree and 360 degree. That is more than 1/2 second. See, up to this point it is exactly 1/2 second. But if you can see here, if this is taken as an average level, then it is crossing the 1/2 cycle. So what it is between 180 degree and 360 degree of the AC input signal. Okay. Class C. Output of class C conducts for less than 180 degrees. That is not even 1/2 cycle also. Okay. So less than 180 degree of the AC cycle, the Q point is below the cutoff. So if this is the load line, somewhere here below the cutoff point, you are having the Q point. And see this, you will be getting only a small portion of the positive half cycle or negative half cycle, whatever it is, but not even one complete half cycle. Okay. So if you can just summarize here, comparison of amplifiers. See, for class A, operating cycle is 360 degree, class B it is 180 degree, and for class AB it is 180 to 360. Class C it is less than 180, that is not even 1/2 cycle. Okay, and class D it is pulse operation. We shall not discuss about AC signal here, it is for pulse operation. And coming to power efficiency, if you see, class A power efficiency is 25% to 50%. And class AB it is between 25 and 78.5. Okay. Basically, class B power amplifiers will give efficiency of around 78.5%. So since class AB is compromised between A and B, so class AB power amplifiers efficiency will range between 25 to 78.5%. Okay. And efficiency of class B is typically over 90%. Now efficiency, what does efficiency actually mean? It's a ratio of output to input power. The lower the amount of conduction of the amplifier, the higher the efficiency. Right. So first we shall discuss about class A power amplifiers. Okay. Again, class A power amplifiers, they have got two types: series fed power amplifier, class A power amplifier, and transformer coupled class A power amplifier. So in series fed, there is no transformer in the circuit. That is, you are not going to use any transformer. RL is in series with VCC. That is, load resistor is connected in series with VCC. There is DC power drop across RL. So efficiency will be 25% maximum. Okay. That is, in series fed class A power amplifier, you are not going to use any transformer. The load resistor RL is directly connected in series with the DC supply VCC. Okay, and there is some DC drop across RL, so we'll be having a maximum up to 25% of efficiency only. Okay, coming to transformer couple, the load is coupled through a transformer. As the name suggests, you're using a transformer for coupling the load. Okay, DC drop across the primary of the transformer is negligible compared to the previous case where you'll have DC drop across RL. The DC drop across the primary of transformer is very negligible. So there is no drop across RL. So compared to series fed, in transformer fed you will have better efficiency. That is around 50%. Right. So two types, series fed and transformer couple. In series fed, you will not be using any transformer. Simply you will be connecting RL in series with VCC. Since there is a drop across RL, you will be having less efficiency, that is 25%. Transformer couple, you will be using a transformer for coupling between the amplifier and the load. So what? There is a minimum drop or negligible drop across the transformer, primary winding of the transformer. So you'll be having more efficiency compared to series fed. So let us go to the series fed class A power amplifier. Okay. So this is a circuit diagram of series fed class A power amplifier. If you see here, you are just connecting this RC. That is, RC is nothing but RL here. Okay. It is connected in series with VCC. And you have one base resistor RB connected to VCC. See here. Shows a series for class A amplifier. Circuit is seldom used for power amplification due to its poor collector efficiency. As we have seen in the table earlier also, it has got very low efficiency compared to all other power amplifiers. So what it is very rarely used for power amplification. Okay. DC load line of the circuit we'll just see it. When an AC signal is applied to the amplifier, output current and voltage will vary about the operating point Q. Okay, just see this. So this is a DC, this is a load line. Okay. Now if this is a variation of input signal, if this is a variation of the VCE is output voltage and this is a collector current IC. Okay. So you can see the variation of as how VCE changes. Okay. As VCE decreases, IC will increase. Okay. And as VCE increases, IC will decrease. Again, as VCE decreases, IC will increase. Okay. So the DC, when an AC signal is applied to the amplifier, output current and voltage will vary about the operating point Q. So in order to achieve the maximum symmetrical swing of current and voltage, the Q point should be located at the center of the DC load line. As you see here, if a Q point is located at the center only then the amplifier will be able to conduct for the complete one full cycle. Right. So in this case, operating point IC equal to VCC by 2 RC and VCE equal to VCC by 2. Right. See, if you look at this diagram, if you apply KVL to this collector emitter branch, VCC equal to IC into RC plus VCE. So if this is IC, RC is nothing but RL as I told. So VCC equal to IC into RL plus collector emitter voltage is written as VCE. Okay. So VCC equal to IC into RL plus VCE, or taking VCE to the other side, IC into RL is equal to minus VCE plus VCC. So IC is equal to minus VCE by RL plus VCC by RL. Okay. So IC is equal to minus 1 by RL into VCE plus 1 by RL into VCC. This is one equation. Now similarly apply KVL to base emitter circuit. Base emitter circuit, what do you have? VCC equal to IB into RB plus VBE. Okay. VCC equal to IB into IBQ into RB plus VBE. Or simply you can say IBQ is equal to, since VBE is equal to 0.7, VCC minus 0.7 by RB. This is what IBQ. And this is obtained by applying KVL to CE circuit, that is collector emitter circuit. And by applying KVL to base emitter circuit, you will get this equation. Okay. So the corresponding collector current is given by. Now once you get IBQ, what is ICQ? ICQ is nothing but beta into IBQ. Corresponding collector to emitter voltage is VCEQ. Once you get ICQ, VCQ is nothing but VCC minus ICQ into RL, because VCC equal to IC into RL plus VCE. So VCEQ is nothing but VCC minus ICQ into RL. Okay. So if we look here, this is what at the operating point, whatever the collector emitter voltage and collector current you have, that is nothing but VCEQ comma ICQ. Okay, this would be the graphical representation of class A amplifier. Okay. So as the input signal changes, as the input signal varies as a sinusoidal waveform, similarly we'll have VCE and IC also, variation in VCE and IC. So using RMS signals, generally how do you define power? We could use either RMS signals or peak signals or peak to peak signals also. We shall see three possible formulas or definitions. Okay. Using RMS signal, basically P0 power, AC power delivered to the load may be expressed as P0 AC equal to VCE RMS into IC RMS. This is using RMS signals. P naught AC equal to VCE RMS into IC RMS. So P naught AC equal to, because VCE equal to IC, VCE equal to, VCE RMS can be written as IC RMS into IC RMS into RC. This is VCE RMS. Okay. So P naught AC power delivered to the load is RC is given by P naught AC equal to VCE RMS into IC RMS. So replacing this VCE RMS by IC RMS into RC, what do you get? IC RMS, so it is IC square RMS into RC. So P naught AC can be written as this one. So from this, or in other words, if you rearrange, if you replace this IC by VCE by RC. So from this equation, what do you get? P naught AC from this one. P naught AC is equal to VCE is nothing but, IC is nothing but VCE by RC. So VCE into VCE by RC, you'll get VC square by RC. So P naught AC equal to VC square RMS by RC. This is the expression using RMS signals. The same if you want to use peak signals. Okay, AC power delivered to the load can be expressed as VCE peak into IC peak by 2. Because usually RMS value is given by VRMS is always equal to V peak value by root 2. Okay. So VCE RMS is nothing but VP by root 2. Similarly, IC RMS is nothing but IP by root 2. So you'll get VCE peak IP by root 2 into root 2. So what you're getting this 2. Okay. Because see, P naught AC using RMS is what? VCE RMS into IC RMS, isn't it, from the previous thing? Okay. But what is VCE RMS? VCE RMS is nothing but V peak by root 2. VCE peak by root 2 into what is IC RMS? It is IC peak by root 2. So what, on multiplying these two, you will get VCE peak into IC peak by root 2 into root 2 is 2. Okay. Similarly, again by rearranging the terms, you will get P naught AC equal to IC square P by 2 into RC or VCE square by 2RC. Isn't it? Then using peak to peak signals. Peak to peak signals means it would be 2 times. So the AC power delivered to the load may be expressed as P naught AC is VCE peak to peak into IC peak to peak by 8. So VCE peak is nothing but VCE peak to peak by 2. Okay. So if you want to write this in terms of peak to peak, how do you write VCE peak to peak by? VCE peak is nothing but VCE peak to peak by 2. So it is by 2 root 2 into peak to peak by 2 root 2. So on this multiplication, you will get 2 root 2 into 2 root 2, you will be getting 8. Okay. See, you can write here. Generally, P naught AC is VCE peak by 2 into IC peak by 2. Okay. This, it is by root 2. Yeah. Root 2, root 2. Okay. So if I want to write it in terms of peak to peak, VCE peak is how much? VCE peak to peak by 2. Okay. If you divide peak to peak value by 2, you will get 1 peak value. So already you have here 2 root 2. Similarly here, IC peak is nothing but IC peak to peak by 2. So replacing that, you will get IC peak to peak by 2 root 2. So you'll have VCE peak to peak into IC peak to peak by 2 to 4. 4 into root 2, you'll be getting 8. So P naught AC equal to VCE peak to peak into IC peak to peak by 8. Similarly, again rearrange the terms, you'll get this is equal to IC square peak to peak by 8 into RC or VCE square peak to peak by 8 RC. Either of the expressions can be used to calculate the P naught AC. So using RMS signals or peak signals or peak P signals, you have got different formulas for calculating the P0 AC. Now coming to maximum AC output power, P0 max is given by VCE peak to peak into IC peak to peak by 8. Okay, so VCE peak to peak is nothing but VCC. IC peak to peak is VCC by RC. So on multiplication, we'll get VCC square by 8 RC. Okay, IC is nothing but VCC by RC. So you'll have VCC square by 8 RC. Now, whereas DC power supplied is given by VCC into IC. So VCC into IC is given by VCC by 2 RC. So on multiplication of these two, you'll be getting VCC square by 2 RC. Now, maximum collector efficiency is given by P0 maximum by PDC into 100. So P0 maximum, that is AC output power, is given by VCC square by 8 RC divided by PDC is given by VCC square by 2 RC. So VC square, RC getting cancelled. You have 1 by 8 divided by 1 by 2. So you'll get simply 2 by 8 into 100. That is nothing but 1 by 4 into 100. So you'll have 25%. Okay. This is how you calculate efficiency of series fed class A amplifier. First we'll calculate maximum AC output power. Then what is the DC power? Then ratio of these two, that is maximum AC power output by DC power supplied, that is PDC, into 100 will give you the maximum collector efficiency. So maximum collector efficiency of class A power amplifier, series fed power amplifier is given by 25%. Maximum is 25% that you can achieve. Okay. So coming to the advantages, see there are few advantages as well as disadvantages for series fed class A amplifier. Coming to advantages, circuit is simple to design and also to implement. Okay, the load is connected directly in the collector circuit. As we have seen, it is connected in series to VCC. So the output transformer is not required here. Output transformer is not necessary. So this makes the circuit bit cheaper. So less number of components are required as load is directly coupled. You will be having only less number of components. So what are the advantages? Circuit is simple to design, right? Circuit is cheaper as well as less number of components are required. Coming to disadvantages, the load is connected directly in collector circuit, so it carries the quiescent collector current. This causes considerable wastage of power. So main disadvantage of series fed class A power amplifier is there is considerable wastage of power. Next, power dissipation is more. Second disadvantage is power dissipation is more. So power dissipation arrangements like heat sinks are required in case of series fed class A power amplifier. Output impedance is high, hence circuit cannot be used for low impedance loads. Thing is, it cannot be used for low impedance loads such as loudspeakers. Then the last one is efficiency is very poor due to large power dissipation. As we discussed earlier also, efficiency of class A power amplifier is too low. Okay, too low. That is compared to the remaining power amplifiers, efficiency of class A power amplifier is just 25% only. Okay. So next we shall discuss about transformer coupled class A amplifier. Now in class A power amplifier, the load can be either connected directly in the collector, that is as we have seen for series fed, or it can be transformer coupled loads. Okay. By using the latter method, it is always preferable to use transformer coupled only for two main reasons. First thing is, transformer couple will permit impedance matching. First advantage of using transformer couple is impedance matching will be good. And secondly, it keeps the DC power loss small. That is, wastage of power will be less in case of transformer couple class A amplifier. Okay. So if you look at this circuit diagram, see here. Here you are using a transformer coupling. There we have just connected this RL directly in series with VCC. Whereas here, we'll be making use of a transformer. Okay. So the primary, under zero signal conditions, the effective resistance in collector circuit is that of the primary winding of the transformer. So primary resistance has a V line, is a vertical line rising from VCC as shown in figure. When signal is applied, the collector current will vary about the operating point in Q. Just here. Yeah. So if you see here, the Q point is again located in midpoint only, because for class A it is at midpoint. Okay. Now if you see this, this is what variation in output voltage VCE. As VCE decreases, IC will increase, and similarly increase in VCE will have a drop in IC, and then decrease in VCE will cause increase in IC. Okay. See, primary resistance has a vertical line rising from VCC. So primary resistance of generally of this transformer winding will be very less. Okay. Now transformer action. First, before going into detail about the efficiency of class A transformer coupled class A amplifier, first we shall have few basics about transformer action. Okay. Transformer used in collector circuit is for impedance matching mainly. So RL is a load connected in secondary of the transformer. See this RL. RL is a load connected in the secondary. RL dash is a reflected load in the primary of the transformer. RL dash is a reflected load. So number of times in turns in primary are N1, number of turns in secondary are N2. So let V1 be the voltage developed across primary and V2 be the voltage developed across secondary. And I1 and I2 are the primary and secondary currents. Okay, you can just see here. This is primary winding and this is secondary winding. N1 are the number of turns in primary, N2 are the number of turns in secondary. V1 is the voltage across primary winding, V2 is voltage across secondary, that is output of transformer. Then RL is the load resistor and RL dash is a reflected, okay, RL dash is a reflected load in the primary. Now we shall see what is the relation between all these terms. Okay. As we know, V1 by V2 equal to N1 by N2 and I1 by I2 equal to N2 by N1. So what do you get? V1 by I1 is equal to, V1 is nothing but V1 by I1 equal to, what is V1 from this 2? V1 is equal to N1 by N2 into V2. This is V1. Okay. By I1, by, what is I1 from this? N2 by N1 into I2. So what do you get? If this will be reciprocal when it goes to numerator, so we'll get N1 by N2 whole square into V2 by I2. Okay, N1 by N2 whole square into V2 by I2. But V1 by I1 is what? RL dash. Yes or no? So V1 by I1, that is on primary side, it is RL dash equal to N1 by N2 whole square into V2 by I2 is nothing but RL. So RL dash is equal to N1 by N2 whole square into RL, where N is now, if N is equal to now ratio of number of turns in primary to number of turns in secondary, then what do we get from this? RL dash is equal to N1 by N2 is nothing but N. So you have N square into RL. So RL dash is equal to N square into RL. Right. So if you analyze the circuit, the power loss in primary is assumed to be negligible because its resistance is very small. Okay. Input power under DC condition is given by P in DC, or DC input power is nothing but P trans TR DC, that is VCC into ICQ. So under maximum capacitor of class A amplifier, voltage swings from VC maximum to 0 and current from IC max to 0. So VRMS is what? VRMS is equal to VCC maximum minus VC minimum by 2 root 2. Okay. This is voltage. VCE maximum minus minimum by 2. Since you are taking RMS value, you will divide it by root 2. So VC maximum minus VC minimum by 2 root 2. So this is nothing but VC maximum by 2 root 2, because VC minimum is nothing but 0. Since VC minimum is equal to 0, so you will get VC maximum by 2 root 2. What is VC maximum? Again, maximum value is VCE. Okay. So maximum value is VCC. So, 2 VCC. You could just see here. Yeah. See. Maximum value is 2 VCC, minimum value is 0. Similarly, collector, it is 2 IC and 0. Okay. So maximum value is 2 VCC. So it is 2 VCC by 2 root 2. So it is VCC by root 2. This is VRMS. Similarly, IRMS is IC maximum minus IC minimum by 2 root 2. IC minimum is nothing but 2 into ICQ by 2 root 2. So it is ICQ by root 2. So these are the VRMS and IRMS values. Now what about P0 AC? P0 AC is nothing but VRMS into IRMS. So VCC by root 2 into ICQ by root 2. VCC into ICQ by 2. Root 2 into root 2 will give you 2. So collector efficiency is nothing but P0 AC by P in DC. So collector efficiency is, what is P0 AC? VCC into ICQ by 2. Okay, and what is P in DC? Say P in DC we have seen here. P in DC is given by VCC into ICQ. So substitute that here, VCC into ICQ. So VCC, this is what? VCC into ICQ by 2. This factor is nothing but P0 AC. And P in DC is VCC into ICQ. So ratio of these two will give you 1 by 2. So collector efficiency is nothing but 1 by 2 into 100, that is 50%. So transformer coupled class A power amplifier, the efficiency is given by 50%. Maximum collector efficiency is 50%. Okay. Then we have got advantages as well as disadvantages even for transformer couple. Advantage, as we have discussed earlier, signal power, loss of signal power is very less. There is no loss of signal power in base or collector resistors. And excellent impedance matching is achieved. Gain is high as well as DC isolation also is provided. So what are the 4 advantages? No loss of signal power. Okay, no loss of signal power. Then excellent impedance matching, high gain as well as DC isolation is also provided. And disadvantages? Low frequency signals are less amplified comparatively. Okay, using transformer coupled class A amplifier, you will have better efficiency compared to class A series fed amplifier. But the thing is, here low frequency signals are amplified to somewhat lower extent. Okay, hum noise is introduced by transformers. That is quite obvious. Using transformers will be having noise. Then transformers are bulky and costly, and also poor frequency response. Frequency response will be poor because, as I told, low frequency signals are being less amplified. So we'll have poor frequency response. Coming to application, circuit is where impedance match is used, where impedance matching is the main criteria. Okay, and these are used as driver amplifiers and sometimes as output amplifiers. So basically, transformer coupled class A amplifiers are mainly used where impedance matching is very essential. That is where this is a basic requirement. You go for transformer coupled class A power amplifier. So these are used as driver amplifiers as well as output amplifiers. Okay, this is about transformer coupled class A amplifier. Right. So far we have seen what is the main need for power amplifiers. There is large signal amplifiers. Then what are the basic types of power amplifiers? There is classification. Okay, and then coming to class A power amplifiers. Again, what is the 2 types of class A power amplifiers based on the mode of coupling. Okay, that is series fed and transformer coupled. Series fed, we have seen the efficiency calculation, that it is a maximum efficiency that a series fed amplifier can provide is only 25%. And coming to class A transformer coupled amplifier, it can provide maximum efficiency up to 50%. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.